Einstein, during the 1890s, was not yet concerned about clocks at all. But he was, already in 1895, as a young man of 16, very much concerned with the nature of electromagnetic radiation. Even to his untutored imagination, something was wrong with the customary conception of radiation as a wave in a static, substantial ether. Suppose, he thought to himself, that one could catch up with a light wave, as classical physics might imply. Then, like a surfer riding an ocean wave train, I borrow a rather distant metaphor, seeing as surfing was not too famous in Switzerland, he would see the electromagnetic field unfold before him like the undulating regular hills in space, but utterly unchanging in time. This, however, corresponded, as mentioned before, to nothing ever observed in the laboratory and nothing that the theory of electricity and magnetism could offer. 4 years later, in 1899, at the ripe old age of 20, Einstein was still agonizing over the nature of moving bodies and electrodynamics. To his beloved Mileva Maric, he reiterated his interest in measures of space and time by Helmholtz, one of the great scientists of the 19th century, and Einstein's sense that the naive ether theories would simply have to go. He wrote to his girlfriend, "The introduction of the term ether into theories of electricity has led to the conception of a medium whose motion can be described without, I believe, being able to ascribe physical meaning to it." One of the greatest scientific devices ever invented, the interferometer, was created by an American scientist and precision instrument maker, Albert Michelson. Let's take a look at a slightly updated version that uses a laser to do what he did with more ordinary light. So what we have here is an interferometer, a version of what Michelson invented back at the end of the 19th century. And it works, as we've discussed, by having a wave that hits a mirror and then returns, and the outgoing and incoming wave interfere with one another. And when crest meets crest and trough meets trough, it's a strong signal. And when crest meets trough and trough meets crest, it flattens out to no signal. So what we can do with this, and this is what this is designed to explore here, is to measure even tiny differences in the length between the laser, in this case, and this mirror. We can see, in fact, since the wavelength is about 600 nanometers, about 600 billionths of a meter in length, we can measure even a couple of hundred nanometers change in the distance between that laser and this mirror. So in this case, let's turn on the speakers here. We can actually hear the tiny vibrations of this building that are shaking it. Maybe a car outside, maybe somebody walking around, maybe the air conditioning system of the building. And so if I take my thumb and press on this wall, you're actually hearing the motion of this building by 1,000 or so atoms in distance. It's an extraordinarily precise device. Michelson hoped that his new device would actually detect our motion in the ether. It's the analog of saying, I'm moving somehow across the desert on a train, and I want to know which direction and how fast I'm moving compared to the air, which we imagine to be still in the desert that day. You could hold up your finger and feel your motion through it. But what do you do with the ether? Michelson's device was designed to tell you that. How fast am I moving in what direction? Well, there was another possibility for explaining this, and that might be that maybe the ether was dragged with the Earth as it moved around the sun and spun on its axis. But there seems to be no evidence for that. You can't drag the ether very effectively. For instance, you could do an experiment, as the physicist Fizeau did, of moving water through a pipe and seeing if it changed the speed of light just proportional to the velocity of the moving water. But it didn't. The air doesn't seem to be able to drag the ether, and yet we can't see ourselves moving through the ether. Well, if it's not static and it's not being dragged with us, then what's it for? Does it even exist? Electricity and magnetism, Einstein concluded, would be definable as the motion of true electric masses with physical reality in a truly empty space. The ether, that centerpiece of 19th century physical theories, the main concern for some of the greatest physicists of the last 50 years before 1905, was simply gone.